Hi everyone. So today we will be talking about the Raoult's law. I hope Henry law and whatever we have discussed related to that is clear to everyone. And now we will be talking about the Raoult's law. Raoult's law is basically about the volatile nature of the liquid and the solute. Okay. So there are three things that we are going to study in the Raoult's law. Starting with the first one, what we are going to talk that I'm first going to do. We will be talking here about what is volatile and what is non-volatile. You all know that volatile means the thing which has the capabilities to move out of the container, right? To get evaporated faster. And non-volatile is it is not going to move up. Let's say if I take an example of I'm having a container in which I'm having some water, and to the water I've added some salt, right? Let's say we're having NaCl. So when we have added some salt to this water, you all know that water is a volatile thing, right? So slowly this water will move out of this container. But if we talk about this salt, that is NaCl. NaCl is a non-volatile thing. Now because it is a non-volatile thing, it is going to stay there in the container. So when these type of non-volatile solutes are added to the volatile substances or the solvents, the solution formed will have a lesser vapor pressure present above its liquid. Okay, I'll draw it for you all so that you all can understand. Let's say we are having this one container. Not very good at drawing, so please bear with me. And I'm covering this up with, let's say this. This is a cover which I'm using. I'm using this so that whatever vapors will be developed here will not move out of this container. Okay. Now, let's say these red colored dots that I'm drawing here is complete solvent. This is the solvent. Okay. It's the pure solvent. Let's say this is water. Okay, I'm taking example of water. So this time, if by taking the room's temperature or maybe when you are heating it, so by taking that temperature, slowly you know that this water vapor will start moving up, creating a vapor pressure above it, right? So that pressure which is created is not affected by any of the factor present inside this liquid because we're not having any solute to this. We've not added any solute. So whatever vapor pressure is being developed inside this, will draw. So these are, let's say, the vapor pressure. Okay, because these are the particles which are moving or which are creating the vapor pressure, right? And okay, what is vapor pressure? I think some of you might be confused with this, so I'll tell you. Vapor pressure is that pressure which is developed over this liquid at an equilibrium state when the same amount of vapors are pressurizing on the liquid and same pressure is given by the liquid on the vapors. Okay, at equilibrium we study always the vapor pressure. Okay, and now in the second container, see, I'll be drawing the red dots also, but I have left some space, and in that space add some, let's say, green color. This is the solid. Let's say this is salt. Okay. Now, to this I've added this NaCl, which is salt, right? This is water. This red one is water. So to the water, I've added NaCl, which is salt. Now you all can see the upper layer is only having 3 dots which are red in color. That means this time if the vapor pressure will be created, that will be lesser than the figure 1 which I was showing. So from this, what do we draw the conclusion? The conclusion is that as you've added a solute, this is what is keeping out. Am I drawing any kind of green dots here? No, right? I'm not drawing any kind of green dots here. That means this time, this is a non-volatile solute that we have. This NaCl is a solute and which is non-volatile. That means it is not going to move out. And because it is not moving out, the another water molecules cannot come and occupy this position because once this Na will leave, only then the other molecule of water can come here. Na? But this Na is not leaving the position. Like if I am sitting here on this chair, and if I'm not leaving my chair, how can the other person come and sit here? Because I'm a non-volatile solute, I'm not leaving my position, the other person cannot come and take it, right? But if I am a volatile solute, then I will quickly quickly get vaporized out of my chair, and then the other water molecule can come and sit at my position, and after some time, by taking the heat from the surrounding, or if you will heat it will start getting evaporated, right? So that means by the solute, if it is a non-volatile one, the vapor pressure is getting reduced. I hope now it's clear to you all. And that is what we study in Raoult's law. So Raoult's law says if you are not adding any kind of solute to the solvent, and the solvent is the volatile one, if it is a volatile one, in that case, the vapor pressure is directly proportional to the mole fraction of the solvent particles. So I can also write this equation like this. I'll take the constant K and like this, right? Okay, right, 1 and 1. Now listen to me very carefully. 1A, 2B. Now see, always remember, no matter from which book you're studying, all the books take 1 and A as the solvent, and all the books takes 2 and B as the solute. So whenever I will be writing 1 and A, always make up your mind that I'm talking about the solvent. And whenever I'll be talking about 2 and B, that means I'm talking about the solute part, right? So this time, because I'm only saying that I'm having the solvent, which is in a liquid state, right? So which is volatile. That means all the molecules are quickly moving out of the container, right? So this time, all the pressure in this figure, as you can see the figure 1, in the figure 1, you can see all the red dots are moving out and nobody is there to control these red dots, right? So here the pressure is purely because of the water molecule. So can I say that x1, that is the mole fraction, is pure 1? Why? Because the fraction is always, let's say if I'm having a pizza, okay, so this is one piece, and from there I can cut the slices. Now in the same way, there is this mole fraction out of 1. Now because I've not added any solute to this, you can write it. See, x of A plus x of B will be equal to 1, or it can be x of 1. I always say this as x, okay? And this mole fraction of A plus mole fraction of B will be 1, because mole fraction is always started by 1. So if I say that B is not present, this is 0, B is not present means solute is not present. If solute is not present, that means only one thing is there, that is solvent. So x is equals to 1, right? That means I can put x, this mole fraction, as 1. So this equation will become P is equals to K of 1. I think that's clear to everyone. Now I can say that this K is now becoming equal to P, right? Because only one solvent is there, this pressure which is equal to K, that means I can write this also as P1 of naught. This is P1. Okay. Why P1 not I'm writing? Because this is purely this pressure inside this figure 1. The pressure is purely because of the solvent. So I can write K is equals to P1 naught. Now put and substitute this value here. Okay. Now P is equals to K, in place of K I'll be putting P1 naught. So P1 naught is mole fraction of 1. Okay. This is the equation which we get from the Raoult's law. That means when you are having a solute which is non-volatile, which is a solid, because NaCl is a solid, right? So we study this in that way. So this is Raoult's law when one which is a solute is non-volatile and solvent is volatile. Okay. This is that case. I hope that's clear to everyone. And now we'll discuss one graph related to this also. But I think this is given in your NCERT book also, so it will be helpful for you all. Now see, I'll be taking the same equation as we've already studied. P1 is equals to P1 naught mole fraction of 1, right? Now if I will be comparing this as I was comparing in the Henry law, right? Y is equals to mx plus c, because y is equals to mx plus c. In maths we started that this is the equation for straight line, right? So now we know that there is nothing about the c, right? That means c is 0. That means intercept is 0. That means the line is not going to start from here. The line is going to start from the 0 point. That means from here the line will start. Now I don't know what should I put here on the y-axis and which parameter I'll be putting on the x-axis. But from comparing here, I can see that y is coming equivalent to p. That means pressure I have to take there, right? And this mx is equals to this, which is mole fraction, right? Okay, I'll write it. This is the mole fraction of the solvent, right? So I'll be writing x of 1, or either a you can write, or you can write 1, either one, whatever you want to write. Now, what is this? How do I know how to draw this line this much or this much or this much? How do I know this? Because this m value, which is here, this m value is the slope value. Now, this m value is the slope value. Slope is going to tell that how much tilted the line will be. Okay, and you know that tan theta is equals to m, which tells us about the slope. So in this case, m is equals to p1. If we compare the two equations, I'll be getting m is equals to p1 naught. So this is the value of p1 naught, the pure pressure. Is it clear to everyone? I hope this will be clear. If you will watch the complete video, trust me, you will understand this concept in a very good way. Okay. So this was a concept which is there in your NCERT book. Now I will give you one add-on to this, which is not there in your NCERT book. This was in terms of Raoult's law, but there is another scientist, Graham. According to Graham, he talks about evaporation, or you can also write it in terms of vapor pressure. Right? Either you can talk it in terms of vapor pressure. He always says, Graham says that vapor pressure is inversely proportional to square root of density. He has a different way of thinking, like I tell you how. He says, Graham says that if you're having only solvent once, okay, this is solvent, and now to this solvent, let's say I've added some salt, okay. The salt whatever. You all know that if I've added the salt to this water, now the density is going to increase. Now, because in the solution the density is increased, this density increase, that means the vapor pressure will go down, evaporation will go down. I hope now it's clear. So this is what Graham have a different kind of point, but yes, both the things are saying the same thing. That as you're adding something which is non-volatile, which is not adding up to the vapor pressure, obviously the vapor pressure is going to go down. I hope that's clear to everyone. And for more videos, please stay tuned to the videos. Please make sure that you hit the like button, you subscribe my channel, and also press the bell icon, because when I will be adding the next video, you will not get the update for that if the bell is not pressed. Please make sure that you all press that button also. And yeah, this is it for today. Please revise it. And now we will be meeting some other day with some other session ahead. Till then, take care. Bye bye all of you. Bye.